Okay, let's start. So today we will continue to talk about FPGA board, and we will also talk about the SRAM and the cache. So we introduce the basic blocks in an FPGA board, including a lookup table, a reconfigurable interconnections, and we also present several detailed implementations of each type of components. So here is a reconfigurable interconnection with two LRU or configurable logic blocks. So these are the slices, including the lookup table, the carry logic, the mux, and then the latch or flip-flop. So this is another copy of an implementation. This is the third copy of implementations. And the different implementation, of course, have a different ratios between the lookup table, carry logic, and the masks, and the flip-flop. In order to support more inputs, typically we connect two lookup table units together so that we can, here each of these only have 5 inputs. But if we have 6 inputs here, we need a double of them. So this is the one example to show how can we support a 6 input logic on a 5 inputs lookup table. We need the answer is very simple. We just need 2 of them. These are the physical layout of those lookup tables. And this is, how can we design a AND or OR gates by those lookup tables. This is the the inputs, and these are the outputs. This is the binary format of the inputs. So we can use the Vivado software to do the simulation, because these are the Xilinx FPGA boards. And we also need some I/O cells so that we can actually apply the input and receive the output from the FPGA board. And there are multiple types of I/O interfaces. For example, the output logic blocks is one of them. It implements the registers to improve the system clock to output timing and support a single data rate and a double data rate reception of the data. So it can receive the data from the rising clock. This is the single rate data, a single data rate, and it can also receive the data from both the rising edge and the falling edge. So in one cycle, it can receive 2 pieces of data. This is so-called a double data rate. Double data DDR is a very common method to improve your throughput on the I/O interface. So this is the example of the I/O interface. The most important part on the current FPGA board, modern FPGA board, is of course the interconnection. It includes some local interconnections local networks and global long lines so that you can actually connect different parts on the FPGA board together. So there are several types of global, so-called global routing lines. Different components have different performance, of course. Different, LANs here have different frequency, but also they have different overhead. Overall, if you want to achieve higher throughput or higher frequency, you need to pay larger power consumption. So you need, when you design your circuit, the first question is that whether you need double lines, for example, here. Double lines is very fast, but it also introduces extra power consumption. If you design some Internet of Things, small devices, so maybe this is not the right choice. So this figure summarizes the transistor scaling. The x-axis here is the age. So this is the time. The y-axis here is the density of the transistor. You can see that we actually integrate more and more transistor on the same die or on the same chip. This is so-called Moore's law. So the Moore's law predicted that maybe 4 years or 2 years the transistor number on the same die doubles. But again, it's really difficult for us to integrate more and more transistor onto the same die. This is because actually it's difficult to fabricate so many transistors uniformly on the same die. This is the first issue. More importantly, the second issue is the power consumption. So even you have a lot of cores, for example, 100 cores, you cannot simply power up them because you don't have such large power budget. The current power density on the chip is even larger than that in a nuclear plant. So you can see that the power is, the real limitation for the transistors. So instead of fabricate the whole chip in a 2D die, people started to do some 3D integration. Why they want to do that? The answer is simple. Because with the scaling of your transistor, the transistor size becomes smaller and smaller, and the transistor speed becomes larger and larger. You become faster and faster. However, the interconnections become slower. Why? Because the V's of your interconnection, the V's of the interconnection becomes smaller and smaller. In the normal CMOS chip, the wire is actually fabricated by copper lens. So with narrow V's, the resistance of the wire becomes larger and larger. The resistance per unit become larger and larger. That's the reason why you have larger IC delay. RC delay. The R here indicates the resistance, and C is the capacitance. Actually, you also have a larger capacitance, but the resistance become more and more significant. So that's the reason with the scaling of the process technology node, the interconnection delay goes up and the gate delay goes down. So now we have maybe 10 nanometer. So this problem becomes more and more significant. This is the gap. Remember that we have a lot of interconnections here. So this trend has a larger impact on the FPGA board. As a result, because your transistor becomes more and more smaller, as I said before, it's really difficult for you to fabricate all the transistor uniformly. So you have more reliability issues. Then you need to do a lot of testing, verification, validation, because your circuit simply becomes more and more vulnerable to those variations. The cost of developing a chip becomes larger and larger. That's the reason why, originally we have a lot of startups in this industry, in this business. Now only major company can do that. For example, Intel, AMD, ARM, NVIDIA. So the design, the real chip design becomes, we don't have too many chips nowadays. That's the reason why people pay more attention on the FPGA blocks. So here we have this much market for the FPGA, because we have we don't have a application specific chip because they are very expensive. The people who care about the performance or power consumption started to use the FPGA design here. And interconnection dominant the area and the frequency of the FPGA. So the transistor scaling actually hurt the performance of FPGA because the interconnection becomes slower and slower. Besides the the larger power consumption and the slower speed of the current FPGA, we also have a lot of crosstalk problem. For example, if you have two parallel interconnections, signals may mess up here because of the crosstalk issue. You have different solutions. First, reduce the frequency, which can help you to improve the reliability. But nobody wants to do that because that will hurt your performance. So one possible solution is that make the whole chip in a 3D structure. This is a 3D structure. By a 3D structure, you have a shorter vertical interconnections. Of course, the interconnections here are reconfigurable. Shorter interconnection means less RC delay, and you have a better performance, lower power consumption, and you also have a higher bandwidth. It seems that this method can benefit everybody, but actually, because you need extra fabrication steps, so the fabrication cost goes up. So nothing comes at free. You have to pay something eventually. So now I think 3D structure becomes more and more important for FPGA design. People even design a 3D interconnection for the FPGA. So originally you only have a 2D connection like this. Now you can actually go to another layer. So the interconnection of the 3D interconnection of FPGA board becomes more flexible. I think nowadays you can buy these designs. And we can allocate all the memory element to one layer and all the logic layer to another all the logics to another layer so that you can separately optimize them. And then between them you have a programmable interconnection. So this is the model of the 3D FPGA. Any questions? So we don't have a lecture on Wednesday because it's the Wellness Day. So the next lecture will be on next Monday. So we can continue on the SRAM. Unlike the flip-flop or latch, which can be used as the register, SRAM is a more dense memory elements. So we can use the SRAM to store a larger capacity of data. So you can see that, again, because of the Moore's law, CPU performance scales linearly with the age, but memory speed only slightly increases over years. So you can see there is a gap. In order to avoid frequently accessing the DRAM, the very slow DRAM, we need SRAM as a buffer, as a cache. So this is the SRAM. We talk about the flip-flops and the latches. They can be directly integrated to your circuit. They can serve as the registers, but they are not the real memory arrays. We can also access the DRAM, which serve as the off-chip main memory. Nowadays, you can buy 32 GB or 64 GB, even on the same DIMM. So they are very large, but also very slow. So in order to mitigate the performance gap between them, we need a SRAM to serve as a cache. So in the CPU, it's so-called cache, but in the FPGA, it's called on-chip memory. This structure is a so-called memory hierarchy. The lower level has a cheaper price, larger capacity, so they can help you to store more data, larger capacity of data. If you have a large movie, of course they should be stored in the SSD. But when you're watching the movie, when you are watching the movie on your computer, the data will be fetched into your main memory. And assume that you have a GPU. When the GPU decoding the movie data, the data should be in the cache. And when you GPU actually processing a particular piece of data, that particular piece of data is actually in the register file of your GPU. So in this hierarchy, at a higher level, you have a larger bandwidth, faster speed. but a smaller capacity because the register may only have maybe 128 byte capacity. Cache is about several K bytes. Again, your main memory has GB. Nowadays, the SSD has a TB. So this is the scale of this storage medium. These three layers is managed by the hardware. Managed by the hardware means that you cannot change them. You cannot modify them. You have no influence on them. Some hardware controller can do that. But the disk, or even larger magnetic disk, is managed by the operating system. For example, Linux. By modifying some Linux code, you can actually manage your SSD disk or magnetic disk. But you can never modify the cache, the main memory, and the register files. So in this figure, we have the static memory and the dynamic memory. The static memory can be used to implement the cache, and the dynamic memory can be used to implement the off-chip memory here. We will introduce them separately. The philosophy of the cache is very simple. We just divide the entire memory into blocks. Each block costs you several bytes. For example, each block is 64 bytes. Why we need to do this? Because we need to fetch multiple blocks into the register file. Remember, the register file is only 128 bytes, so that's the reason we prefer a block smaller than that value. For example, 64 bytes, so that we can fetch 2 blocks into the register files. We can also temporarily buffer these blocks into the caches. So when we read a block to the core, besides reading this data to the core and fetching this data and sending it to the core, we can temporarily store the piece of data in the cache, so that maybe next cycle the core still want to have the data of this block. So instead of fetching it from the main memory again, we can read the data from the cache. And compared to the DRAM, of course, the on-chip cache is faster. So in this way, we can save some latency cost. And this is so-called temporal locality, because in different cycles we request for the same data. And we have another, this is so-called a temporal locality. We have another type of locality which is actually the spatial locality. The spatial locality means in this cycle I need the block n. It's very likely I need the block n plus 1 in the same cycle or in the next cycle. This is so-called a spatial locality. Why this may happen? Because in the C++ code, we have a lot of loops. For example, the for loop. It's very likely we execute some loop and have some array. Calculate something, compute something on the array. So in this way, it's very likely we have this spatial locality. The n can be the index of the array. So we have the block concept, which is the size of the minimal granularity of the data we fetch from the DRAM to the core. Frame means has the same size as the block, but a frame is a physical concept. It's how many blocks or how many frame the cache can hold. So one frame can hold one block. So if we can find that piece of data, it's called a heat. If we cannot find that piece of data in the cache, this is called a miss. And we can calculate how the frequency of miss and the frequency of heat. This is so-called a miss ratio or heat ratio. The latency of a heat operation means the heat time or heat latency. The latency to mitigate a miss means the miss penalty. We need to fetch a block from the DRAM and store it in the cache. This is so-called miss penalty. And if the cache is full, we need to pick up an unimportant line to kick out that line and store the useful line. This is so-called replace that block. So here is one example. Assume that the block size is 8 bytes. So these are 8 bytes requests. We have 6 requests. And this is the main memory. This is cache. So we draw the cache larger, in a larger size. It doesn't represent the real cache has a larger capacity. I just want to show you a more clear picture. But actually the cache has a smaller size compared to the main memory. So when we first read the first request, of course it's a miss because we have nothing in the cache. And then we fetch the data from the DRAM and store the data in the cache. Again, I would like to remind you, each block here is 8 bytes. 8 bytes means from 0 to 7 is in this block. But the first request only need the first byte, which is a 0, right? And then the second request comes. It requires the number 4. Luckily, we have this 4 in this range. So we have a heat here. Third time we request this byte. Unfortunately, we have no this block in the cache. We have to read it from the main memory and store the data to the cache. So this is only 1 byte. If we fetch 8 bytes from the DRAM, it's the 10120 to 10127. So it's a range, it's 8 byte. So for the fourth request, we have a miss because this number is larger than this range. So we fetch another 8 byte. This 8 bytes indicate from 8 to 15. And then for the fifth, we have a heat because this number is actually in this range. And for the last one, we have a heat because it heats in the first block. So in this way, we have a 3 requests heat in the cache. We also have a 3 misses. And the heat ratio is 50%. Miss ratio is 50%. So I would like to introduce one metric to evaluate the performance. So the metric is so-called average memory access latency or time. Average memory access time. So if cache heat is a 10 cycle, memory access time is a 100 cycle. This is a very typical value because there is a 10 times latency gap between the cache and the DRAM. So what if we have these much miss ratio, 50%, 10%, 1%? If 50%, if we have a 50% miss ratio, which means 50% times accesses will have a miss, will have this much latency. So 50 multiply 100. Another 50 have this 10 cycle. This is my average latency. So if 10% will miss, then this is 0.1. This is 0.9. If 1%, this is 0.99. This is 0.01. So you can see that with a smaller miss ratio, the average memory access latency significantly reduced. Again, I didn't change anything. I still use the same capacity of SRAM, the same capacity of DRAM. This SRAM still have the same speed, and the DRAM still have the same speed. Only if I have a smarter algorithm to improve this miss ratio, to reduce this miss ratio, I can significantly improve the average memory access latency. Again, sometimes we have a multiple level cache. Not only L1 cache, we also have a L2 cache. So I change this model extend this model into 2-level caches. If the L1 cache cache latency is 5, L2 is 20, memory access is 100. If I have 20% miss ratio in the L1, 40% miss ratio in the L2. What's the memory access average access latency? If the L1 have a 20% miss ratio, 80% will hit in the L1. So 80% will hit in the L1. And for the other 20%, this miss ratio, this misses 20% misses here. Among this 20%, 40% will go to the off-chip memory, because the miss ratio of L2 is 40%. And among this 20%, 60% is actually hit in the L2. So I use 0.6 multiply 20 here. So in this way, I can get this value. You can see that this value is smaller than this one, but larger than this one. It's very difficult to improve your miss ratio to 1%. That's a very difficult job. But again, if you can have more levels of caches, you can still improve your average memory access latency. So we have a lot of techniques to improve the average access latency. Considering that nowadays we have a lot of big data applications, which means that it's really difficult for the data heat in the cache. We need more such techniques to improve the average access latency. Any question? So if no question, I hope you can make some progress on your projects so that after this week, we will have the midterm updates on your projects. So the Wednesday in this week have no class because this is your wellness day. After that, we will, you need to do some presentation to make some progress on your projects. To explain what's the difficulties in your projects. What's your possible solution to overcome that difficulties? Any question? So if you have any question, please email me. Otherwise, we can stop today. Thank you very much.
Thank you.
Thank you.